Rehse. I wanted to go over some problems that we were talking about at the end of Chapter 2's Lecture 5. So there were a bunch of problems that I had embedded for you in the PowerPoints that I posted online, and I said you can go through them on your own, but it just occurred to me that you'd probably like some examples of these things worked out. So I'm just going to go through these problems and work them out on my tablet here. And then you can follow along and see if the way I'm solving it is the way you would have solved it, or if you had no idea how to solve it, then you can actually watch these as kind of a structured way to tutor how it is I think you should be working through problems. Okay, so let's go ahead and jump in. You can see that the last problem that we left off on was this example of a train. So on the screen here, I'm going to be showing you, I'm showing my tablet. So it says a train of mass 55,200 kilograms is traveling along a straight level track at 26.8 meters per second. Suddenly the engineer sees a truck stalled on the tracks 184 meters ahead. If the maximum possible braking acceleration has magnitude 1.52 meters per second squared, can the train be stopped in time? So what we want to do is using the given acceleration, can we compute the distance traveled by the train before it comes to rest? So that's what we are going to be trying to do. Let's see if we can do it. I'm going to get rid of that bar at the bottom there. Okay, so using the given acceleration, which is here, which they told us is this, can we compute the distance traveled by the train before it comes to rest? If that distance is greater than 184 meters, then we know for sure that it's going to hit the truck. If it's less than 184 meters, the train can be stopped in time. So that'll be our strategy. Let's go ahead and do it. You will see that I have listed for you the 5 equations on the right side of the screen. This is just for a while there, just so you can keep these equations in view and know what we're doing. So let's go ahead and try to work this problem. Remember what I said, the first thing you really want to do is make sure you draw a sketch, right? So really important that you draw a sketch here. So I will come up with a sketch, and you don't have to be a great artist. I certainly am not, but here's a little train, and here is an axis. So the important thing is I'm going to call this the plus x direction. Remember, one of the things I said you had to do was draw an axis and indicate what is the positive direction. I'm going to indicate to the right is the positive direction, and I'm going to say that it's starting off at 0. So let's say that x naught equals 0 meters. We know that that's true. What else were we given in the problem? Remember, so you draw a sketch and start to list what you know. We were given, well, we know that it starts somewhere. So we weren't given that it starts at 0 meters. I am going to choose that it starts at 0 meters, and then I would like to know where it winds up. So again, if you look, nowhere in this problem does it say x naught equals 0. You need to know to be able to do that, okay? But we were given some other things. We were told that v naught, the initial velocity, is 26.8 meters per second. All right, so that's great. What else were we given? So here's going to be the trick to this whole problem. Make sure you guys are watching this carefully. I'm going to even switch to a different color here for you, just to make it helpful. Now we have to write the acceleration. Note we don't write a sub 0 or a naught because there is no initial acceleration. This is chapter 2. All the accelerations are constant, so there is just one a. X can change, so there's x naught and x. The velocity can change, so there's v naught and v. Acceleration does not change, so I just write a, not a naught. But what is the acceleration? If you are not careful, and just go through and say, oh yeah, Dr. Rehse, I see the acceleration. It's here, 1.52 meters per second squared. And now you're feeling pretty good about yourself because you think you've got the problem solved. Look at that very carefully. I did something wrong. What did I do wrong? The acceleration is acting to slow down the train. So the acceleration has to be a negative acceleration. I really went over this in class. If you're traveling in the plus x direction and you have a positive acceleration, that's going to make you go faster. If you're traveling in the plus x direction and you want to slow down, you need an acceleration in the negative x direction. So the key to this whole problem was an acceleration of negative 1.52 meters per second. If you don't have that negative sign in there, you're just doomed from the start. Nothing else you do from this point on is going to possibly ever be right. So you've made a fatal flaw at the very beginning. So really pay attention to that sign. Put in a note. Pay attention to signs. This is a negative acceleration. It has to be a negative acceleration. It just has to be. Okay, so now the train is going to be moving down the tracks, and it's going to, at some time later, wind up down here. It's at its new position. What do we call its new position? Well, we were asked to figure out how far it goes, so I don't know what x is. That's actually what I'm trying to solve. X equals question mark. Sometimes I just write that in like that, x equals question mark, because that tells me that's what I'm looking for. Do I know anything else in this problem? Oh, no, Dr. Rehse, I don't see anything else listed. No, not true. One very important piece of information, and this is the trick to solving physics problems, is you have to understand what information is in this problem. What else do I know about the train when it has skidded to a stop? I know its velocity, because by definition, when it has skidded to a stop, its velocity is now 0 meters per second. Look in the statement of problem. Anywhere in there, does it say anything about 0 meters per second? It does not. You need to know to do that. You're looking for points where it's not moving, and then you can insert 0 meters per second. Okay, we have it. So what we know, if I try to do a little survey of this, is it looks like we know x naught, and we'd like to know x. We know v, we know v naught, and we know a. And now you can look at the equations, and do we have any equations that have all those variables in there? We do. We have this one right here. It's why I like to, when I'm solving problems with you guys, I like to list the problems on the right side of the page, so you can kind of look at your variables, look at what's given, and then which equation can you use? Well, that's the right equation. So we can use the equation that v squared equals v naught squared plus 2a x minus x naught. You have to be able to do a little algebra to rearrange this in terms of x. So let's just kind of rewrite it this way. And that says that v squared minus v naught squared divided by 2a equals x minus x naught. So hopefully you all see that, yes? But we know what x naught is. It's 0. So this equals x minus 0, which just equals x. Now we have an equation for x in terms of v, which we know, v naught squared, which we know, and a, which we know. So now, and only now, do you plug in the numbers. You do your algebra first, get into the equation into a form where you can do something with, and now I'll plug in the numbers. So hopefully you have that equation written down. I'm going to go ahead to the next slide and write those numbers in. So it looks like 0 squared minus 26.8 meters per second squared all over 2 negative. Did you forget your negative? No, you didn't. You remember you need to use that negative sign. Negative 1.52 meters per second squared. All right. And that's all going to be equal to x. So now you get on your calculator, calculate. This looks like negative 718.24 meters squared per second squared. And that's divided by negative 3.04 meters per second squared. Note there's a negative sign in the numerator, negative sign in the denominator is canceling out. If those negative signs don't cancel out, you've done something wrong, because look at the picture. You know that as the train is traveling in the positive x direction, it has to wind up with a positive coordinate of x. If you wind up with a negative x, that tells you made a mistake. That's not the kind of thing you say, oh, negative, positive, whatever, it probably doesn't matter. No, it does matter. If x is negative, that means it's moving to the other side of the page. It's going in the positive x direction. I have to get a positive x value. And I do, because I have negative 718 and negative 3, and those negative signs cancel. And you can calculate that out. So that winds up being positive 236.63 meters, which I will just round to positive 236 meters. 3 significant figures. Can the train be stopped in time? No, it cannot. With that acceleration, it travels 236 meters. It saw a truck 184 meters ahead. It cannot. So I will say no, it cannot stop in time. Okay. Very, very simple problem of that sort. I guess I don't have to pause and wait for you to go on, because it's a video. You can pause at any time you want. You can pause me. I'm going to move on. I hope you join me. Okay, here's an example. Another example we can do together. This is an automobile. An automobile's velocity increases uniformly from 6.0 meters per second to 20 meters per second while covering 70 meters in a straight line. Can you find the acceleration and the time taken? Fair enough. All right, so let's take a look. How would we do this? First off, what do you know? What have I told you to do or taught you to do? Read the problem carefully. An auto's velocity increases uniformly from 6 to 20 while covering 70 meters in a straight line. Find the acceleration and the time taken. So what do you know? I would say, let me switch to a different color here. Oh, I'm on green, that's good. I'm going to say you know its initial velocity. V naught is 6.0 meters per second. Let's draw a little car. Here's a car. It's got some wheels. It goes like this, and it's going to a new location. So I know its initial velocity, V naught. I know its final velocity, V, because it's speeding up to 20 meters per second. So I know that. So I know the velocity when it's over here. Now, it takes 70 meters to do that. That tells you you know x naught and x. You see, look in the example problem. You see 3 things, 6, 20, and 70. So you think you know 3 things, but you don't. You know 4 things, because you know that x naught equals 0 meters. Well, you don't know that. You choose it. You choose. I am choosing to say that where it started is 0, and you have to do this. You need an initial coordinate and you need a starting coordinate. You know it covered 70 meters. Look, you could have called it 100 and 170. The problem will work right. You could have called it 200 and 270. The problem will work right. As long as the change is 70, the problem will work. In physics, we tend to set one of them equal to 0 if we can, because it makes the math just a little bit easier. So I'm going to choose to say it starts at 0 and ends at 70, because then that tells me what x is. I'll go back to green. That tells me that x equals 70. Oops, I'm sorry, I should write it here. X naught equals 0 meters. X equals 70 meters. So I know x naught and I know x. Right? You don't know 3 things, you know 4 things. Make sure you write them down, right? Okay, what comes next then? What don't you know? What do I not know in this problem? I do not know the acceleration. No idea. And they're asking us to find that. I don't know the time it takes. And they're asking us to find that as well. So those are the things that are not given. Those are the things that I want to know. Okay. I've read the problem carefully. I've drawn a crude sketch, but that's enough for me. I've indicated what I know and I've made a list. I've indicated what I don't know and what I'm looking for. At this stage, I feel ready to look at the equations and say, which equation can you use? So here are the 4 principal kinematic equations. There's that first one, V equals V naught plus AT. I cannot use that because I don't know A and I don't know T. You cannot use one equation that has 2 things you don't know. I'm looking for an equation where there's 1 thing I don't know and I know everything else. Okay, here's this one. let's see. I think I know X. I know X naught. Ooh, this is looking good. I know V naught. I don't know T. Oh, and I don't know A. And I don't know T. So that equation's out. Too much stuff in there I don't know. How about this one? Do I know V? Yes, I do. Do I know V naught? Yes, I do. Do I know A? I don't. Here's my unknown. But I know X and I know X naught. I can use that equation. And technically, this last equation too, I know X, I know X naught, I know V naught. I'm looking for T. I could use that equation to solve directly for T. So for the first part, finding the acceleration, I would just use this equation right here and just solve it. And I'm not going to do it because I don't actually have the numbers written. I just wanted to show you how to set it up. But it's something 20 meters per second squared equals 6.0 meters per second squared plus 2a that you're looking for, and then 70 meters minus 0 meters. And then there's a. Just solve that equation for a, and you have it. All right. If you wanted to solve for the time, you can do that. Maybe use this equation right here. And then you would say something like 70 meters minus 0 meters equals 1/2 20 meters per second plus 6.0 meters per second times t, and you solve for t. All right. That'll get you the acceleration and the time. And I think I can leave it there because you guys will be able to do that much math. Okay. Very good. Review questions. All right. I wonder how many of you were doing that work at home. A sprinter runs 400 meters around a track. She does this in 50 seconds. Again, pretty good time. 2 questions for you. What is the sprinter's average velocity? And what is the sprinter's average speed? You guys have now been in my class long enough to know that average velocity and average speed are not the same things. But it's okay. You know how to solve for both of those. Let's try to do the average velocity first. Average velocity is usually written V, whoopsie, whoa, that was weird. Sorry about that. V bar, right? That's the average velocity. And we learned that this is the, wow, I have no idea why it's doing that. That's really funky. Huh, interesting. I must be leaning on something with my hand, this weird tablet. Oh, okay, I have no idea what it's doing. Let's just try that down here. So V bar equals the displacement divided by the time. Sorry about that weird tablet thing going on there. Sometimes it's a little too touchy for its own good. Okay, so the displacement equals like x final minus x initial over delta t, which is 50 seconds. But now think about it. Where does the sprinter finish compared to where she started? She started at the starting line. She finished at the starting line. So her net displacement is 0. So the average velocity is just 0 meters divided by 50 seconds, which equals 0 meters per second. She did not wind up moving anywhere, so her average velocity was 0. Half the time she was going in the positive direction, half the time in the negative direction, even though she was traveling in a circle. 0 meters per second. Does that mean that she was not running at all? No, of course it doesn't mean that. Her average speed is not going to be 0. Clearly it's not 0 because she's quite fast running around the track. So let's take a look at that, how you do that. We saw that average. I'm going to try to turn that off. I don't know what it's doing. Oops. Okay. So we saw that the, oh, sorry, flicking through here. Again, the tablet is doing some weird things with my hand. I apologize for that. The average speed is equal to total distance over time. Not the same thing. Her total distance was 1 loop around the track, which was 400 meters. Again, the total time was 50 seconds. So her average speed was 8 meters per second. Not the same thing. This is a perfect, simple question that illustrates what's the difference between average velocity and average speed. And if this is not clear to you, then you're kind of missing the point of all those lectures we had. Go back, review all the material, and just remember, we're not trying to trick you. These are just things you need to have in your mind. This is the physics. Remember, physics is not going to be a thing where I say, take the equation for average velocity and plug in the numbers. I'm asking you questions to see if you know things like that. Do you know the difference between average velocity and average speed? Can you reach into what you know, pull it out, and then apply it? I give you the equation, but you need to actually know when these equations are used. It's really, really important, okay? Okay, so we didn't go through these questions, so I wish we could have had time for those, but we don't. Let's just get to the review questions. Actually, maybe we do have time for that, so we can go ahead and look at it. So let's do the in-class questions, which is fine by me, even though I've already ruined it for you by showing you the answers. But in which of the following cases is the acceleration 0? When is the acceleration 0? A car increases its speed from 0 to 30. Well, if you're increasing speed, that clearly is a change in velocity. It cannot be that. A car decreases its speed. That's still an acceleration. Acceleration is any change of velocity. So it cannot be that. A car goes around a curve at a speed of 30 miles per hour. Now, you might think it is 3 because, oh, the speed doesn't change. But remember, acceleration is not a change of speed. It's a change of velocity. Velocity is a vector. It looks like this. As a car goes around a curve, its velocity vector does this, does it not? Is that velocity vector changing how it's oriented in space? Yes, it is. Even though its length, which is the speed, doesn't change, its orientation changes, which is a change of velocity. Velocity is a vector. So a car going around a curve at a constant speed is still accelerating because the velocity vector changes direction. The only one of these that is a constant acceleration is backing out of a driveway in a straight line at a constant speed of 10 miles per hour. That's a 0 acceleration. The velocity does not change. Pay close attention to this question and make sure it makes sense for you. Here's a question about looking at the velocity versus time graph. There's only 3 options. Which scenario is portrayed by the graph? The car starts from rest and accelerates. It then travels at a constant velocity before slowing to a stop. Well, this is showing at the beginning, velocity is 0, velocity versus time. So at the beginning, the car starts from rest. So car starts from rest, it could be 1. Car starts from rest, it could be 2. A car travels at a constant velocity, it cannot be 3. This is a car starting off at rest for sure. All right, so it's either 1 or 2. So let's take a look at the rest of the problem. It starts from rest and accelerates. Well, acceleration means the velocity is changing. Is this velocity changing? Yes, it is. So it looks like it could be 1. This one says it then travels at a constant velocity. So this leg right here is showing the car moving with some constant non-zero velocity. In the answer 2, it says it stops for a while. If this car is stopped for a while, somewhere in there the velocity has to be 0. Nowhere during the trip is this velocity 0. So it cannot be number 2. So the correct answer has just got to be number 1. A car starts from rest, it accelerates, it travels at a constant velocity for some time, and then it slows to a stop. And that definitely is the correct answer. Okay? All right, so we've done that. Now, review questions. I want to go through one more question of what happens when you graph some things together. So this is another graph of velocity versus time for a body moving along a straight line. I've got a couple blank pages here to work with, so you're going to need to remember this picture. So it is asking us, what is the acceleration AX at t equals 11 seconds? So let me go to a different color here. How about blue? So here is 11 seconds. T equals 11. So they want to know what's the acceleration right there. Note, the acceleration is not on the page because this is showing velocity versus time. It doesn't show acceleration. We're going to have to do a calculation. What is the acceleration at t equals 3 seconds? That's right here. T equals 3 seconds. Okay, so let's do the first one first. Oh, and then of course, see how far does the body travel from, go to a different color here. How far does it travel from t equals 12, which is here, to t equals 14, which would be here? What's the distance traveled during that time? So let me show you how to answer these 3 questions. Let's do the first one. What's the acceleration at t equals at 11, which is this point right here? Well, remember, the acceleration is the tangent to a line on a v versus time graph, velocity versus time graph. So the acceleration is tangent to that line. Let me first ask you, so we're going to have to draw a tangent to that line. Let me first ask you this question. At that t equals 11 second, is the tangent to that line positive or negative? Right? You need to be able to do that. So the tangent is this line right here. Is the slope of that line positive or negative? That is negative because the rise over run, the rise is negative, the run is positive, so that is a negative slope. And you know it's negative because it's pointing down, right? That's a negative slope. So that is a negative acceleration. So whatever answer you get for A had better be negative. All right, so we know it's negative. And then what do? Well, we know that the acceleration then is defined to be v final minus v initial over t final minus t initial. So this equals your slope. And this equals rise over run. So to do this, you actually have to pick out 2 points. So what I'm going to do is any 2 points along that branch that go down, I can use. So I'm going to use this point right here. So this point right here is 40 meters per second, and we'll call that v initial. And that is actually happening at 9 seconds. And that's like t initial. Or if you want, this will be v naught, and this will be t if you're doing it the way our book does it. And then I need another point. Well, I'm allowed to pick an easy point, and any point on that straight line will do it. So I'm going to pick this point right here. Because why am I going to do that? Because at this point right here, it says v final equals 0. Or just v. T final equals 13 seconds. And now here I can't set t equal to 0 so it doesn't go away. So I better call that t naught as well. You do have to do that once in a while. And I'll just use that as t then. So the later time, remember, has no subscripts, and the earlier times have subscript 0. So let's go ahead and plug this into this guy then. So that, oh boy, I wonder why it's doing that. Very curious. All right. So this guy, then it says it has to equal v minus v0, and this will be t minus t0, as we just went through on the other page. So this is 0 meters per second. Oh, wow, I don't know what it's doing there. It's very 0 meters per second minus 40 meters per second, all over 13 seconds minus 9 seconds. So this to me looks like negative 40 meters per second. Note that negative sign hangs on, equals 4 seconds. Do that math, negative 10 meters per second squared. It's a negative acceleration because this thing is slowing down. Remember the first thing I did with you, the answer is it was pointing, it had a slope that was down. That has to be a negative acceleration. So we got a negative acceleration. What you get from the graph has to agree with the numbers. So the acceleration at time 11 seconds is given by that slope, and that's negative 10 meters per second squared. The next question is what is AX at t equals 3 seconds? Well, t equals 3 seconds is that point right there. The velocity is constant during that time, So we know that the acceleration is 0 meters per second, right? This is, just look, this is a tangent to that line. The slope of that tangent line is 0. So you know that the acceleration is 0 meters per second squared. You see that the velocity curve is not changing. That tells you the acceleration has to be 0. So that's going to be the answer to part B. I would say V is not changing. Slope is 0 meters per second squared. So AX equals 0 meters per second squared. All right, last thing to do. How far does the body travel from t equals 12 to t equals 14 seconds? To do this, we need to calculate the area under the curve. All right, so I'll go back to green. Part C, the area under the curve of a V versus T graph is net displacement. And you're going to be doing this in the lab. You're going to actually be measuring these quantities with the IO lab. You're going to have a velocity versus time curve. The software will integrate it for you, and you'll find that that's going to be equal to the total displacement of the IO lab. So what we mean by the area under the curve is anything between the 0 line, is here, and the red curve, which if I shade it in, it's just going to look like this region here. Okay, there's nothing to shade in between 13 and 14 seconds because it's already 0, right? So it's that little triangle there. I need the area of that little triangle. That is the area under the curve, and that's how I get the displacement. So if you could zoom in a little bit on that thing, you will see that the area under the curve, it looks like a triangle. Kind of looks like this. It starts at 10. It goes to 0. It starts at 12 seconds, and it goes to 0 at 13 seconds. I am just showing you, oopsie, whoops, why is it doing that? That's weird. I am just showing you a zoomed in, hang on, let the screen catch up with me, right? See that triangle I grew? Do you see how it's starting at 10 right here? And it's winding up at 13, or it's starting at 10. It's going to 0, and it starts at 12 and winds up at 13. That's the triangle that I'm trying to show you guys. Great. So what's the area of that? Well, that's a triangle. That's the area of a simple triangle. I think you guys know how to do that. It's 1/2 base times height for the area of a triangle. So the area of this guy is 1/2 of the base, which is 13 seconds minus 12 seconds, times the height, which is 10 meters per second minus 0 meters per second. So that looks like 1/2, 1 second times 10 meters per second. Units cancel. You can make that, feel free to make that sound with your voice when you do the crossing out. I always do. And this is going to be equal to 5 meters. And 5 meters is the total displacement of that object from 12 seconds to 13 seconds. It is the area, the shaded area under the curve. Kind of looks like that. On the other curve, the red line was something like this. All right, so the area under the curve is going to be the displacement of a velocity versus time graph. Okay, well, I think that's enough, guys. Fine. We are done with those problems. So I just wanted to provide these for you. I hope you find some of it helpful. Maybe a lot of you are not even looking at it at all. That's great. But if you find this was at all useful, please go through it. Go as slow as you want. Rewatch if you want. If you have questions, we can still talk about it during office hours. So that's all I have for you now. So I'm going to stop recording, and I'm going to see all you guys in class. All right? Take care.